Yeah, for sure. Hello, everyone. This is Hamza from York University. I just missed the first introductory part. So from Toronto under the lockdown. Our next talk is like another industry talk on by Xiasong Lou from Blackline. So the title is Concurrent User Modeling, an Alternative Approach to Classic Queuing Theory. So it's a very interesting talk. I was looking forward to this. So let's have it. Please go ahead, Xiasong.
Thank you, Hamza. Let me share my screen. Here's my, oh, this is challenging. This is, okay, here it is. Sorry about that. View slideshow. Okay, so hi, thanks for coming. My name is Xiasong Lou. I'm a performance engineer at Blackline. Been here for a while, being in the industry for a while. This is the first time I come to this conference. Thanks for your invitations. Today's topic is about concurrent users. There's a little bit more words on the slides than I hoped for, so apologies for the crowdedness. In one of my previous talks to a different crowd, I talk about concurrent users and how to model it, and people ask me, why do you care? Okay, interesting question. First of all, you probably are not a performance engineer for very long. And second is, why do we care? So here's the thing. A common misunderstanding of concurrent user, and we see it a lot in our real life experience, is people ask you to test a system under a certain amount of concurrent users, and they thought it's a good idea. Concurrent users is a random variable. If you test it under a static value, it's not a proper test. We have other ways of describing and testing random variables, and we'll discuss it later. But the common mistake here is don't treat concurrent user as a static value. So back to why do we care? Well, first of all, we know that things slow down when you have to queue up, and concurrent user is one of the key reasons why queuing theory is in place. When you have more resource, when you have less resources than the concurrent number of requests, some of the requests gets queued, and they will be executed whenever the resource becomes available, and that wait time in the queue is reflected in the response time, and that's why you slow down. So if you simulate the concurrent users properly, you get the proper end-to-end response time. If you don't simulate it properly, you get a wrong response time. Sometimes you get it artificially high, sometimes you get it artificially low. There are other issues that created by concurrent users. For example, there was a little panel discussion in previous hour that we talk about the number of concurrent connections to other servers that is caused by the concurrent user generated by the end-to-end user. And there are other faults that are not very easily exposed by unit tests, deadlocks, race conditions, and so on and so forth. All these things are triggered by concurrent users. Now, granted, we know that we cannot test all the possible concurrent user scenarios because we have a time constraint in our performance test window. However, we wish to test as real as possible what the product would experience under production environment. This is what this talk is about, is how to test the real concurrent user, the random variable under production workload. So before that, let's complain a little bit because lots of tools are actually exact that. They use the default setting, which leads to the wrong concurrent user results. And we will show you what do we mean by wrong. And there's always a way to use the tools correctly. So in this context and in many other similar tools, similar discussions, I always say that don't blame the tool. The tool is a tool. It's up to the person to use the tool properly. If you want to use a screwdriver to hammer a nail, you can. It's your responsibility to do it right. So a little bit of theoretical background for concurrent users. We have very, very commonly known mathematical tools. To get the average numbers, you have Little's law. To get the exact probability of individual concurrent user state, we have Markov chain. Now, if we have a Markov chain solution, then all the probabilities of all the possible concurrent user states are calculated, which is, problem solved. In reality, the Markov chain solutions looks a little bit intimidating, if I may use the word. So here we have an example. This is the MMC queue. This is probably one of the simplest queue you can find in Markov chain analysis. And here's the solution. It's actually not that bad if it comes to it, but looking at the equation, it doesn't appear intuitive to the numerical value of certain. For example, if people give you parameters, ask you what P0 is, it might take quite a while for you to figure out. It's not intuitive, right? So this is why Markov chain analysis, we don't see many of those in the daily queuing theory analysis, daily performance result analysis. As a matter of fact, there are a lot of performance engineers who claims that I don't know anything about Markov chain analysis. Well, that's an interesting topic, but okay. So we propose a totally different model. So in this model, we look at the problem from a different angle. Instead of server states, we look at the relationships between the client, which is the user machine, and the server on the timeline. So on this chart, we look at the gray area, which is a transaction. So the beginning of the gray area is the request, the end of the gray area is the end of the response. And the white area is user interaction. So people are filling forms, they're playing with the mouse, they're trying to find the buttons, so on and so forth. Now, we have a large number of users doing work on their individual machines from 1 to K. Now, in some areas that gray periods overlap, the system see concurrent user, right? So at the beginning of this chart, all three users, all the 1, 2, and K, all these three users are white, which means none of them are in the server. So the concurrent user state is 0. And a little bit later, you see 1. A little bit later, when client 1 comes in, you see 2. And then pretty quick after that, client 2 goes away, then you see 1 again. So on and so forth. So this, if you look at this, we can model the server's concurrent user states using this model. And this model, a little bit of caveat, is a non-IID model, which is not independent and identically distributed. Because for the single client, the gray areas are dependent of each other. One has to happen after another. These two gray areas cannot happen independently. Among the K users, however, things are independent. Each individual client have their own schedule, own way of doing things, and things are independent. Within the single client, things are not independent. In most of the Markov chain analysis and most of the queuing theory analysis, we assume all the requests are independent, which doesn't apply in this closed network setting. If we expand, if we have infinite users, K is infinitely large, and transaction time is, well, okay, let's say the user interaction time is infinitely large. Then this model approximates the MMCK model in classic queuing analysis. So using this model, we for this crowd, the next few slides should be pretty straightforward. Using this model, we see a Bernoulli distribution. We put them together. We see a binomial distribution. And binomial distribution is still not intuitive because you have the exponential part, and then you simplify it into a normal distribution where you see the average response time. You see the probability of individual state is presented like that. But we see that part is still a little bit ugly, but we look at the where clause where mu equals kt over t and sigma equals kt over t times a little thing. Now that is interesting because mu over here, kt over t, if we recall Little's law, that is Little's law. The average number of concurrent users in the system is Little's law, and this is the expression of Little's law. And sigma equals almost equals square root of mu if the little t is small or capital T is large. When capital T is infinitely large, sigma equals square root of mu, right? So when mu is Little's law and sigma equals square root of mu, this falls back to the classic Poisson distribution. So this is what we like. Poisson distribution is probably the 101 stuff in performance engineering, and we like it. Now, if it is not, T is not infinitely large, then we adjust the distribution by shrinking its standard deviation a little bit, and we know its numerical value. And that is very intuitive because we know it's a normal distribution, and we know where the average is, and we know what the standard deviation is. We have 70%, 95%, 99% mapping. Each corresponds to the 70%, 1 sigma, 2 sigma, and 3 sigma width of near the center. So that's very easy and very, very frequently used chart. So that's the theoretical background, and we run a little bit test to prove that this thing works. This is our raw data. This is the actual concurrent user states change during our 10-minute test. You can see that it's a random variable. It changes the up and down, and we send a static state steady state of 1,000 users. Each has an average response time of 188 milliseconds, and the total think time is on average 15 seconds. So 188 over 15, the number is really small. We expect the result to match a Poisson distribution very well. Okay, so this is let's say this is the real scenario that people want to test. So we run it with the model, we calculate the model compared to our measurement, and this is the distribution. And we see that the green line, which is the model, is almost directly on top of the measured line, which is the purple line. So our model is a very good description of the actual concurrent state. Now, if we do stress test as some of the people that I saw was doing, so this is a little bit of a common mistake that people do. That is because of the limits of their load generator resources, they cut down the think time from whatever production think time is to whatever number they can get away with so that they get the same throughput as what the production is experienced. In other words, in this particular case, we want the throughput to be such and such. To get that throughput, let's cut down the think time. Let's cut down the think time so that we can do the stress test with only 20 threads. Well, we can do that. We do it, and by calculation and by the previous formula, we know that the average mu, average arrival rate, is the same. The standard deviation is much smaller. And this is exactly what we see. The purple line is the so-called stress test. I'm sorry, the purple line is the actual test scenario we want to work against. The green line is the measured stress test that people are trying to mimic the actual case, and we see that the shoulder part is missing. Now, the left shoulder part is where the concurrent user is much less than average. That's probably not a problem, right? The right part, right shoulder of this chart is where you see a lot of high concurrent users in production, but you didn't test it. This is where the problems lie in. If you don't cover that much at a proper ratio, you are actually missing a bunch of potential opportunities to catch bugs. And also, your average response time is probably not correct. We just said that if the numbers, the think times are large enough, and the relative transaction time, response time is small enough, this thing matches the Poisson arrival model, and this is it. There's a utility, I think it was around for more than 30 years by HP laboratories. It's called HTTPerf. And that thing that's a very, very small C code with excellent Poisson distribution simulations. And if you run HTTPerf against our test, then we see that the model and the results are, again, perfect match. But HTTPerf has very small areas of expertise. It does one thing very well, but it doesn't do much other than that. Nowadays, it's no longer a very useful performance testing tools because our websites gets more and more complicated. So it's not, in many cases, it's not relevant anymore. We use HTTPerf as a theoretical studying tools. Now, if you use other tools, you can still do Poisson distribution. However, it's not, usually it's not the default value. So when this model doesn't work, so this model, this model we talk about, depending on the fact that individual users, not individual transaction, individual users are independent of each other. So when individual users are dependent of each other, then we say this model doesn't work. And this is a case where this model doesn't work. So we use Jenkins to run this tool, and the Jenkins has one particular setting that is very, very popular among all the performance test engineers. It's called constant throughput timer. So it says, I will guarantee you a certain constant throughput among that many threads. Don't ask me how I schedule all these individual threads. I just guarantee this constant throughput. Now we run the test, and we see that by achieving the same constant throughput, the purple line, which is the concurrent user levels generated by HTTPerf, is very, very, very different from the green line, which is what the production environment would experience. Now, if you run this test, if you use constant throughput timer as a production reference, then your result will be way off. Furthermore, when we notice that in the on this chart, the purple line rises really high up, more than 35% at 0, which means 35% or more of the test time, there are no users in the system. We don't know how exactly JMeter does that, but we have a guess. We believe in JMeter's case, when you do constant throughput timer, these numbers of threads, they're synchronized. So they're in the system together, and they're out of the system together. And when they are out, all of them are out. That's why you see the 30 very, very high percentage of system idle. And that is a totally different scenario than what the production experience is. And there are other things in JMeter that we explore. on this chart, the actual line is purple. That is what our baseline is. And there's a Poisson random timer. And originally, when the first time I saw Poisson random timer, I believe it was 2.5 or 3 in JMeter. And I was really excited saying that, okay, finally JMeter got something right. And they want to introduce the Poisson random timer. And then I look at the source code and it doesn't seem to be what we expect the Poisson distribution look like. And then indeed, if you test it, you see that the distribution of concurrent users as a result of their random timer is very, very different from what we'd expect as a Poisson distribution. However, JMeter later introduced something else called precise throughput timer. And that thing is actually Poisson. Now, why is it called precise instead of Poisson? Is probably because Poisson, the name is being used. So somebody did do it right, except the good name has been used, that they have to use an alternative name. So, well, the key point of this story is when you look at JMeter, don't just look at the name, and we need to look at what the code is actually doing. Sometimes when they say they're doing this, they're not, and when they're not saying they're doing this, they're doing it. Okay, so all right, so I rushed through the 20 minutes of presentation. I hope there's enough time. So this is the summary. We are talking about concurrent users. We presented, instead of the somewhat of intimidating queuing theory solutions, we have a somewhat, in our personal opinion, a little bit easier solution to model. And use this model, we can do a after the fact validation. That is, after the performance test is done, we can validate that our test is doing what it's supposed to do. Now, with queuing theory, you can do predictions. There's a huge difference. So queuing theory is still much better than ours. Ours is a little bit easier if calculation, if normal distribution calculation is approachable to you. Okay, so 20. Okay, thank you. Not questions?
Okay, great. Thank you, Xiasong. Do we have any question? No? So actually, I myself have like a point, as Andre on the chat actually mentioned. When you remove the think time, basically you are changing your system, which is a closed kind of system, to a kind of open one. And it's no surprise that you see all that drifting in your result, because basically you're changing the system to something else, which is not really representative of that. And another point on the Poisson, usually when we have a large number of customers that they ask questions or requests to your system by a very low probability, always it's safe to actually assume that process a Poisson. So that also goes with your finding on this. And that's why I saw this study very interesting. And a kind of follow-up question on this, we can use this approach in order to somehow imitate the queuing theory for some of these systems at a steady state. What is your thought on if you want to somehow analyze a kind of transient behavior of systems?
Very, very good question. Up to now, I don't have a theoretical approach for transient state. It's a problem that is out of my skill set. What in terms of the actual practical approach, what I do is I arrive first at a series of steady state, and then just do regressions on the series of steady states, trying to come up with a plot, and just say that at transient states, This is the range of let's say we're talking about response time. This is the range of response times you can expect. And usually, if it is homogeneous workload, I think that approach is working. If it is if it is a mixture of a lot of different workload, I don't know how reliable that approach is.
Okay. I guess we are close to the next talk. If we don't have any question, we just can move on to the...
I have a very quick comment, and
Sure.
that is that some of the terminology in JMeter doesn't necessarily comport with what you see in the standard performance or queuing theory literature. So it's necessary to indoctrinate the users, especially students who aren't familiar with this kind of thing, with the mapping between the different kinds of terminology so as to avoid confusion. Maybe not just students, actually. If you're in a setting in which there's a high staff turnover, you need to do that also. The other comment I had was that in some cases you maybe see what you may have achieved by setting your parameters incorrectly is a semi-Markov arrival process with on-off states.
Oh yes, I totally agree with that. Especially on the first part where the JMeter terminologies are really not what we would expect in the literatures.
Thank you.
Okay, so I guess I need to just, can you?
Yeah, let me stop.
Yeah, the sharing so I can share the slide.
I don't know how to stop that though. Stop share, there you go.
Okay, good.